Okay, so what I'm going to do is have an introduction, get a little background on the problem that I'm addressing, description of the simulation, demonstration, and examination of the logic, next steps, and questions. Now, the first thing I should do is apologize to everybody for a number of different things. One is, this is a presentation I gave a year and a half ago, roughly, and so if anybody's already seen it, you can leave for the bar and I'll catch up with you later. Second thing is that everybody here so far has been splitting the atom, and I'm talking about railroading that got started in the United States in 1827, about 40 miles from here. So we're getting down to very elemental things, not the big picture that everybody else has been examining. I'll also say that when I did the presentation before, people said, well, geez, that looks kind of nice, but I don't know if that really represents what a railroad does. So I'm going to take you through a little primer here on kind of the problem we're looking at. So having said all that, okay, so the first thing is that, just a simple problem representation. We've got three shippers in California shipping all over the country, but they have some customers in New York City, and we just show that everybody ships to everybody in New York and ships elsewhere as well. Now, if I were representing a trucking company, what I would be doing is I basically dispatch a truck to handle each one of these loads. Now, one thing I should say is I'm talking about shipments that move in truckload or rail carload volumes. This isn't Amazon that's got the little package that has to go to a warehouse and be sorted and so on. This is moving automobiles or moving washing machines or some large product that is going to take up a full truck or a full rail car. So in any case, if you're a trucker, it's a pretty simple problem. You call a trucker, the trucker drives directly to the customer, it's all done. Well, railroading is just a little bit more complicated. First of all, we're going to start in Los Angeles. We have the three shippers, and somehow or another we have to get the cars pulled together into a yard. So what I show here are three arrows, which would be trains bringing cars in from each of the shippers. And the role of the rail yard here is two things. One is a railroad makes its money by aggregating a whole bunch of little things into a big thing. So the whole idea is instead of having 10 trucks and 10 drivers, you have 100 or 150 rail cars and 2 drivers. So the whole idea of a rail yard is to be able to aggregate these things into larger units. The second thing that you do at a rail yard is to sort them. So all these shippers are shipping to a bunch of different places, some of which are, in this case, Seattle, Chicago, Houston. So we also have a sorting problem that we're looking at a rail yard. So the train now leaves Los Angeles. We'll follow the Chicago route because that's the way something would get to New York, most likely out of LA. Chicago is the #1 terminal in the US, probably in the world, for railroad activities. So we get to Chicago, and again, our train is split up. It's combined with other cars going to different destinations. And so again, we have a Detroit, a New York, a Boston, or whatever on its way to their destinations. Again, we're going to follow the New York bound. So the train's leaving Chicago for New York. Once it gets to New York, we want to split out the customers, 1, 2, and 3. And we also have to drive for Boston, for Detroit, and everything else. So we have all this different. Again, we have to do the switching again. So now the customer gets to, or I should say a train leaves for each of the customers. So the purpose of the simulation that I've been working on is to look at effectively how that operation works. So it's just the switching within a rail yard. So I'll show you a demo in a minute. One of the things that that's basically key here is we have a rail library that makes it very easy to visualize this. I guess one of the things I should say, one of the things I think is a beautiful thing about a railroad is it's all out there. It's all visible and demonstrable. There's not electronics moving around like in a computer. So one of the things I think that really helps in the railroad business is to actually show people the physical process that you're doing, because they can stand, you know, we build rail towers in all the railroad yards so you can watch where all the cars are. And so this gives us an ability to actually see on a very granular level how these things are happening. So let's just examine Chicago. And what we have here is this kind of a view. What we effectively have here, if you can follow the mouse, is down at the bottom we have the main line where the trains would come in and out. And basically we'd have trains arriving into these tracks down here at the bottom, and those tracks are long enough to hold an entire train. But as you can see, there are not many tracks. So what we need then is the ability to sort the cars into a number of different destinations. So what we would do is we'd pull the trains out of the east end or the right end of this lower yard, shove the cars up into this upper level, and then we would sort the cars, and then when we're done, we'd pull the cars from the upper level back down to the lower level, and that's where we'd put our final trains together, go out on the main line. So for the purposes of this presentation, I'm just going to focus on that upper piece of the switching part, not the train arrival, not the train departure, just the switching. Okay, so basically, as I said, the cars, I pretty much said this, cars enter from the right at the kind of bottom of the blue area. They're pushed to the top track. An engine comes in from the left, and then it starts switching the cars. Once there's 5 cars in a track, a locomotive comes in from the right side, grabs the cars, and takes them away. So it's a very simple model, nothing very sophisticated. So let's play trains. It's Christmas time. Everybody has a Christmas tree. You put the train around it. Okay, you don't have to put the train around it because we're play trains now. Okay. As soon as I read it. Come on, come on. Why can't I find can't find the mouse. Here, hang on. Come on. Ah, there we go. That's why I couldn't find it. Okay, so what we have here is just a simple little diagram. You get a sense of the representations you can make of the rail cars, the tracks, and so on. The beauty of the rail model, and again, you know, for people who are seasoned users of AnyLogic, I'll be talking about things that are pretty well known to you, but for people who are maybe new to it, I'll talk a little about the things I find pretty exciting, which are some of the ways of designing the logic and so on. Okay, so we'll run the model here, and what you see is trains coming in, being shoved by a locomotive on the right-hand side there, and that locomotive leaves, and now the locomotive comes in from this side. And I'm slowing it down here because this is kind of the guts of the whole process. So that's a supply of cars, and he's now going to switch the cars down into each of the tracks in the yard. Now, a couple things that I think are pretty amazing about this. In a lot of simulation languages, you're using conveyor belts to pretend that there's some transport operation. Here we actually have tracks, we actually have switches, we have locomotives, we have routes, we have rail cars, coupling, uncoupling, and so on. That's all in there. So what you're seeing here is effectively what is physically done on the railroad, and that is you have a cut of cars, you move ahead, somebody walks along in the car, pulls what's called the cut lever that uncouples the car, the engine stops, and the car keeps rolling. That's what we call kicking cars. Now, what you may notice too is it didn't just take one car at a time, it took as many cars as there were going to a specific track. So it's smart enough to understand that, and that's, again, what you'd actually do in the real thing. So our locomotives just come in. There were 5 cars in that track. It came in, picked up those cars, and away it goes. So let me speed it up so the next train comes in quickly enough. Okay, so again, that engine leaves. One of the things that was interesting in this process as I was setting it up was that that engine would come in and start grabbing cars before they stopped rolling. That's not a good idea. So I had to put in some logic to stop it. Now I should proceed, but slower here. So we have a 2D animation. Here's the 3D animation. So you can obviously move the camera around in any number of different places. You can see all the different activities as the cars get moved. Okay, we'll be just about done there. Kick one more car. So the locomotive now knows it's done, and I kind of like watching this where the engine falls off the end of the earth. Okay. So let us go back to 2D. Okay, so the locomotive's coming in, and by the way, I could highlight any of the cars. I was too slow on that one. I highlight any of the cars and it'll tell me information. So the great thing, again, it's because of the Java logic behind the scenes, there's a lot of richness in the sense that there's objects and methods and so on that are available. I don't know if perhaps you've noticed that the tracks change color if there's a car in them. Well, I didn't do anything for that. The object that is a track knows that, and so it can display differently. So let me go now to, let me just pause this for a minute. We'll go to the logic piece. So this is the logic that's running this model. And to me, I mean, first of all, it's great because it's self-documenting. If somebody says, well, why did that engine come out? Why did that happen? You can physically go to the place where that's happening and figure out how you might want to make a change to it. So I can actually sit down with somebody at the railroad and say, okay, here's how I define this thing. Here's where the engine comes in on the left. It drops off cars. Here's the cars left on the track. Here's the other engine coming in. Here's the engine coupling. And here's the whole logic for kicking the cars, pulling the pin, stopping. Here's the cars rolling into the tracks. Then once there's a certain number of cars, I trigger this locomotive to come in, grab that, and so on. So, and the beauty too is here's the variables and their values. So as it runs, you can actually look to see, you can kind of debug it as it goes because the variable values are physically displayed to you at any time. And if you run the simulation while if you look at the logic while the simulation runs, I should say, then you can actually see different things change in the graphical display. So you can see if it's a true-false, you'll see it flip. You can look at a lot of the elements at the bottom, tell you how many entities have gone through, how many trains, how many cars, and so on. So let's go back to the 2D animation, and we'll finish this guy up. So when I first developed this, what I would do is I just have the engine would come in, and any track that had 5 cars, you'd grab those 5 cars and leave. And then if there's another track with 5 cars, you come back and grab those. And that's not really the way you physically operate the railroad. So what I did then was add the ability to have the logic that it checked to see if there's another track that needed to be picked up. So now one of the things I'm going to do here is I'm going to click on one of these cars. There we go. And here's the information about that car. Again, I didn't do much to get that. It knows what car's next to it on either side, knows where it's coupled, knows what track it's in, and knows what the location is. So now the engine's leaving, and now we have 3 tracks where 5 cars or more are ready to be pulled. So you see it's smart enough to pull ahead, go back, grab the next cut of cars, and leave. So, and down here you can see as the car moves, you can see it updating the status information about its location. So, that's all I intended to do about that. So let's go back to the PowerPoint, if I can find it. Okay. Okay, so I don't think I'll spend any more time on this because we kind of went over it before, but effectively, the neat thing is, you know, that you can focus in with your user on why it has a certain behavior and say, okay, well, if I add this parameter or I add this additional decision step or whatever, I can change the behavior. And say it's self-documenting and so on, which I think is really powerful. So in terms of the next steps, I've been very fortunate. Andre's been a great supporter of enhancing this tool. And so we've worked together on a number of things. We've improved the railcar shapes he mentioned earlier. So we have, he's willing to add 50 shapes to the library to represent different types of railcars. The depiction of track we talked about before, that's been enhanced. There's not right now the smoothness of an import of track information from GIS or CAD, and so that's being discussed. And one of the things I really like to do is to build what I call a higher level rail library. Right now, if you watch the simulation, what effectively is happening was I was telling every object what it should do. So I said the locomotive should leave, that the cars should be placed here, or whatever. And that's not the way a railroad yard's run. A railroad yard is run, take the train, put it in track 5, you're done. That doesn't, so nobody says where to uncouple, they don't say where to put the locomotive, whatever. There's a higher level language that's used in railroading that we kind of feel like we have to teach to AnyLogic. And one of the beauties of AnyLogic is the ability to actually create these custom libraries, which some of the earlier presenters talked about. So instead of, for example, one of the things, if a train's too long for one track, what a yardmaster would do would say, put the train in 5 and double to 6. Okay. Well, to do that, I say he has to know how to uncouple, he has to pull ahead, he has to change the switch, he has to reverse, he has to clear a track, he has to pull away, he has to uncouple, pull away the locomotive, and so on. Right now, I have to say each of those individual steps. And if I could get to a level where I could say, pull into 5, double to 6, then I've got really something that is more relevant to, to the users. So all I did here was just say, there's possibly we can take a lot of that logic and basically put it into, create a new library that is put a train away or kick cars into tracks so that we can now start building higher level models without having to always go down into each of these individual details.